Okay, so when you're solving problems in three-dimensional space for trigonometry, you normally want to, so the main idea is to draw right triangles. Okay, you draw right angled triangles, as many as you can, or you just draw a basically 2D diagrams. Okay, so for example, let's have a look at this one here. The first question is CF. The length CF is this length here. So actually it doesn't even exist, so we need to draw that in here. But normally I prefer not to draw too many things into the main diagram because it's going to get busy. So I will draw a 2D version of what? Of this. This is a rectangle, right? So they note the right angle here, and it's a triangular prism, so that's why this has to be a rectangle, and let's draw that rectangle out. So note that's you have to keep in the same order, DC, and then CE is a bit shorter, so DC and then EF. So that's 4 centimeters, that's 5 centimeters. This is not to scale, but we can work it out. So that's F here, and then we're at the length CF, right? Is a right triangle, which means that for question A, you can just use Pythagoras theorem. Okay, using Pythagoras theorem, you would get CE squared plus FE squared. So essentially, just the two short sides of a right angle triangle equals to the square of the hypotenuse, which is CF squared. So you get 4 squared plus 5 squared equals to CF squared. And so that will be 16 plus 25 equals to CF squared. So that will be 41 equals to CF squared, and CF is positive, so it will just be CF will just be the square root of 41. Alright, so look at question B, the length BF. So now we're looking at BF. BF is actually this length from here to here. So what shape would I draw? Alright, what shape would I have to draw here? In this case, I will actually need to, so I'll base it off of what we know so far. We know CF, okay? We know the length CF here, and what else do I know? I know BC to be 3. So now I will want to draw CBF, okay? And that's a right angle triangle, and I'll highlight the triangle here. It's roughly this triangle, okay? That's like a vertical triangle, but then it's a little bit slanted. We can still draw it out and then see what the sides are. Okay, so for question B here, CBF will look something like that. So FBC, we already found CF to be square root 41, and then BC was 3. Okay, so we can find BF using, once again, Pythagoras theorem. So using Pythagoras theorem, I want that write it again. I'll have BF squared, which is the hypotenuse squared, would be equals to the sum of the two shorter sides here, the square of the two shorter sides. So that'll be 3 squared plus, now square root of 41, when you square this, you just get 41. Okay, so then BF squared would be 9 plus 41, which is BF then would be 50, so square root of 50. All right, if you want to simplify that, you can split that into 25 times 2, because 25 is a perfect square. So that would be 5 square root 2. All right, but either way, square root 50 should be okay as well. Make sure you write the units here as well. Okay, so that's how to find BF. And then the angle BFC, to correct to 1 decimal place. So the angle BFC, well, we've got the drawing here already. So the angle BFC, let's call that angle theta. Okay, so in question C, we're just basically finding that angle theta here. Now you can use many different ways of doing this, because we know the side BF, 5 square root 2. We all know all 3 sides. You can use either sine, cos, or tangent. In this case, I will try using tangent. Right, tangent of theta would be opposite, which is that side there, over adjacent, which is this side here. So it'll be 3 over square root 41, and so theta would be inverse tangent minus 1 of 3 over square root 41. Okay, and you can punch this into the calculator to get the answer, which should be roughly about 25.1 degrees. Okay, next we need to go through 2 concepts, which is angle of elevation and depression and true bearings. Okay, so first we'll go through angle of elevation and depression. So let's say if you are standing over here and we only look at your eye here, right, and then consider that as the eye level. So let's say we'll represent you as a dot, okay, and then you have a cliff, right? You have a cliff, and then there's something at the edge of the cliff. There's something you're really interested in, whatever that is. It's up to your imagination. Now, this point of interest, I call that point P, and this is I call that point B, the base. So when you draw a line between these 2 points, right, the angle from the observer B here, the angle met with the horizontal, this is the angle of elevation. Because you have to look side and then look up, right? So that's angle of elevation. And then from the point of interest here, though, let's say a person of interest, right? So person of interest here, if they're standing at point P, and then in order to look at the point B here, they will need to look straight and then look down. So this is the angle of depression, right? The angle of depression. But note that because these two angles are they're both made with horizontal lines, right? Which means that you can apply the Z rule. See the big Z there, right? The big Z there. Apply the Z rule, and then you can say that the angle of elevation is the same as the angle of depression. Okay, so if you have 2 points like B and P here, the angle of elevation is the same as the angle of depression because of the Z rule, and this is quite handy to use in some of the questions. Next, we'll go on to true bearings here. So when you're dealing with true bearings, the idea is that you will have to have bearing from a certain point A. That means that from the point A, you draw the north line. Okay, and the bearing is always clockwise, counterclockwise for true bearings. Okay, so for example, if I were to have the bearing of, I'll change that one up. If I have a bearing of 100 degrees from point A, right, it means that from point A, draw the north line, and then I need 100 degrees, which is a little bit over 90. So this here would be the bearing of 100 degrees from point A. Let's have a look at some examples and it will make a little bit more sense. All right, let's have a look at example 6 here. A tower is situated due north of a point A. Okay, so tower north of A. We'll start slowly sketching it out. So from a point a tower is somewhere north of it. All right, so let's draw that line first. Normally, I prefer to draw the drawing in the middle actually. So I'll start the drawing somewhere in the middle with a lot of space around it. Okay. Now, north of a point A and do west of a point B. So west of B, that means that the point B is somewhere over here, right? Because west of B is in this direction. So point B is there and the tower will be there. On the same level as, okay, from A, the angle of elevation. So from A, the angle of elevation of the top of the tower. Oh, now there's a bit of a problem. So how do we represent the top of the tower here? Because this is a two-dimensional drawing, right? You can't exactly represent the height in a two-dimensional drawing. So to do that, you would need to use the three-dimensional axes. 3D axis would look something like this: vertical, horizontal, and a diagonal. Now this one would be the y-axis, this would be the x-axis, and that would be the z-axis. So the vertical axis would be the one that is in the third dimension. Okay, and so if we were to use that one here, we have to turn this shape, turn it a little bit in the 3D space, so that, right, it will look something like this. A is here, B is here, and the base of the tower is here. Yeah, let's call that T here. Okay, so, and then now we can represent the top of the tower. So now the vertical line will represent the top of the tower here. I will call that point P. Angle from A, the angle of elevation is 18 degrees. So I would need to draw this thing to A, and then this angle here is 18 degrees. Okay, so note that at this point, you need to see that the triangle ATP is a right angled triangle. So in the 2D space, right, the triangle A, the right angle is at T, and then P is on top, and A is over here. Okay, so it's right angled triangle, and this angle is 18 degrees. let's see. In addition, B, which is on the same level as A, so that's on the flat ground, is 52 meters from A. All right, 52 meters from A. So if we join BA, this is 52 meters. And look, we actually have a 2D version of the diagram, so I can write 52 meters here. And the bearing is 064T. Now, take note of this bearing here. If it's a 2-digit or 1-digit bearing, so for example 6 degree needs to be 6 degree 006 degree true north, always 3 digits for bearings. Okay, so if it's like 18 degrees, it would be 018 degrees true bearing. Okay, so 064 degrees just mean that this the angle between here and here is actually bearing from A. Okay, tower is north of A, which means I draw the north line, and that will also pass through the tower. So then the bearing of B is just here, 64 degrees. Okay, now we need to find the distance from A to the base of the tower is essentially that distance here, right? Because part A is the distance from A to the base of the tower. And we're using the 2D drawing. That's why it's handy to do as many drawings as you can, and one of them will be useful. So for part A, I will use that drawing here. So now that's the adjacent side to the angle 64 degrees, and this is the hypotenuse 52. So I will use the K rule. So cos of 64 degrees would be 80 over 52. And so 52 times it to both sides, 52 cos 64 degrees would be equals to 80. Punch that into the calculator. Would get you 22.795. I like to write more decimal places whenever I can. So that's 80. And then let's see, correct to one decimal place. So I'll keep that value there, but I write the final answer as 80 equals to 22.8 meters. All right, so that's the answer for A. And then the height of the tower. Okay, the height of the tower is actually PT. And look, we already drew that over here, like a little tiny diagram for 2D. A 2D diagram over here, PT. Now we know 80. Actually, let's make it a little bit bigger. Okay, let's redraw this diagram here, make it a bit bigger. So A, P, and T. So T is here, A is here, and that's the top of the tower. This is 18 degrees. Now we've got 80, but I prefer to write the more decimal place, because when you want to be rounded to one decimal place, you need to use at least, my recommendation is 2 more decimal places, okay, in your intermediate working. So now we need to find the height of the tower, which is PT. All right, and that's the opposite, that's adjacent. So for question B, we'll use the TOA rule. Okay, so tangent of 18 degrees would be opposite, which is PT, over adjacent, which is 80, so 22.795. Okay, once again, punch into the calculator. PT would just be 22.795, tangent 18 degrees, and the answer will be 7.4065 meters. And once again, to one decimal place, PT would be 7.4 meters. Okay. Lastly, the angle of elevation of the top of the tower from B. Okay, now this question is a little bit tricky, but we need to use this diagram, this one here again. So let's join PB. So the angle of elevation is this angle here, right? And now what do we know so far? We know the height of the tower, and we need the angle of elevation, but we're missing something here. We're missing BT, right? Let's draw that triangle out, PBT. Right, so for question C, triangle PTB. We want to find this angle here. Let's call that theta. We know PT, which is 7.4065. And we don't know, that's the right angle triangle. We don't know this one, we don't know this one either. So we don't have enough information to work this through. So first, we actually need to find one of these. And looking at this shape here, looking at all the diagrams, I would prefer to find BT, right? Because BT is part of the first triangle here. And I can actually find that using, so that would be opposite. So it would be the sine of 64 degrees and the number 52 here. So first I will find, BT. Okay, I'll redraw that triangle to make things a little bit easier. So that triangle was ATB. Whoops, my bad. It will be AT and B. ATB. Okay, 64 degrees, 52 degrees. So this is 64 degrees. This is 52 degrees. So that's opposite. That's hypotenuse. Using SOH from SOHCAHTOA, sine of 64 degrees is equals to opposite, which is BT, over hypotenuse, which is 52. So times 52 to both sides, then BT would be 52 sine of 64 degrees. And in the calculator, that BT would be 46.737. And in the to one decimal place, BT would be, actually we don't need that because they're not asking for BT. They're asking for the angle of elevation here. So we've found BT. Let's put that into this diagram. 46.737. So that's opposite side, that's adjacent. We need to use tangent. Now we can actually find the angle. So tangent of theta would be opposite, which is 7.4065 over adjacent, which is 46.737. Okay, and so theta would be inverse tangent of that. Just punch the whole thing into the calculator. 7.4065 over 46.737. And the answer should be 9.005 or just 9.0 degrees to one decimal place. This means that the angle of elevation, so go back to this one here, the angle of elevation of point B from the top of the tower is roughly 9.0 degrees. So that's the main, based on the main diagram here. Okay, so make sure to retry these examples because they are very good examples of these two main concepts here.